Good afternoon, dear colleagues, dear friends. I have a great pleasure to welcome you to the Beale Lecture. Thank you all for coming. It's good to see so many of you here, both in person at Newcastle University and virtually. I'm Sanja Petrovic, and I'm the president of the Orar Society. I just have a few housekeeping announcements for you before we get started. Firstly, if you are attending in person, I can say on behalf of the Newcastle University, you are not expecting any fire alarm test today. So if the alarm rings, please do leave the building via your nearest exit. If you're attending virtually and wish to ask questions, our speakers, please post them in the Q&A section on Zoom, and we'll take them at the end of each presentation. The event will be recorded and available on the Society's YouTube channel afterwards. The Orar Society's Beale Medal is awarded in memory of the late Martin Beale. It recognizes a sustained contribution over many years to the theory, practice, or philosophy of operational research in the UK, or to some combination of those areas. And then some more words about Martin Beale. He graduated from Cambridge University with first-class honors in mathematics in 1949. Martin Beale was a pioneer in mathematical programming, which he used to solve complex industrial problems. Today, we are also honoring the memory of another Beale Medal winner, Chris Potts, Emeritus Professor of Operational Research at the University of Southampton, who passed away peacefully on 30th of January this year, 2026. Chris was awarded the Orar Society's Beale Medal in 2021, recognizing over 50 years of outstanding contributions to the theory of operational research, particularly in the area of scheduling of single and multiple machine production systems in manufacturing, including online scheduling, flow shop scheduling, supply chain scheduling, and scheduling with batching. His early work included the development of branch and bound, dynamic programming, local search, and approximation algorithms, and he conducted complexity analysis for difficult problem classes in this area. In later years, Chris developed new theory and methods for problems arising in logistics and transportation, including airport runway scheduling, railway timetabling, vehicle routing, and workforce scheduling. He is internationally recognized as a leading researcher in the field of scheduling, with his work regularly cited by others working on the topic. His contributions extend to healthcare management, where he looked at problems arising in booking patients for surgery and operating theater timetabling, and in location analysis for designing sustainable community health services. Being an avid sports fan, Chris also conducted research into designing match play for the FedEx Cup playoff series, and as an avid sports fan, was a keen supporter of research into operational research in sport. Chris supervised over 25 PhD students to completion during his career and supervised more than 70 master science projects with industry. He, of all people, understood the importance of encouraging and supporting students and early career researchers. And he would have been deeply interested in the work of our first speaker this afternoon. So our first speaker is doctoral winner, Dr. Joseph Farrington. So it is my great pleasure to introduce Joe, the winner of the 2025 Oral Society Doctoral Award. Joe is a data scientist at RL Datix, specializing in the application of machine learning to healthcare operations. He earned his PhD from University College London in 2025 as part of the UKRA CDT in AI-enabled healthcare systems. Joe's doctoral research focused on optimizing replenishment and issuing policies in a hospital blood bank, and won the 2025 ORRS Award for the most distinguished body of research, leading to the award of a doctorate in the field of ORR at the UK University. Joe is joining us online to present his thesis entitled Machine Learning and GPU Accelerated Computing Applied to Platelet Inventory Management in a Hospital Blood Bank. Welcome, Joe, and please deliver your talk, please.
Thanks very much, Anya. Afternoon, everyone. Really happy to be here and very grateful to the Society for deciding whether my work merited the award. So hopefully that's showing up. But if not, someone on the team could unmute and let me know. That'd be awesome. Great. So I'm Joe. This talk is going to be about a couple of lessons from my PhD about how machine learning and OR can sort of help inform one another. And the sort of two ideas here are faster optimization and earlier evaluation. So quick outline. The motivation for this, as Sonia mentioned, I was working in a hospital blood bank looking at managing platelet inventory. And the two key ideas, faster optimization, which is about bringing ML software and techniques to OR to improve the speed at which we can tackle problems. And also earlier evaluation, sort of bringing an OR perspective to sort of a machine learning process and seeing if we can understand the utility of models at an earlier stage before we invest a lot of effort in building them. So I'll start off with the motivation, so managing platelet inventory. So platelets, I think this is sort of probably secondary school biology, but platelets are a component in your blood. They're needed for clotting. You give them to patients if you need them to stop bleeding or to prevent bleeding. There are issues around donor-recipient blood group compatibility for platelets. You have to think about which unit you give which patient, but it's a lot less critical than for red blood cells. You wouldn't expect to see, for example, you know, those really potentially fatal transfusion reactions with certain combinations that you sometimes see with red blood cells. And I was really lucky to work with the Hospital Blood Bank, the transfusion laboratory at UCLH in central London, which is one of the biggest users of blood in the country. And then my work focused on managing platelet inventory at their suggestion. And we originally started looking at, you know, how could we use data science, AI, OR techniques with them, and platelets were really something they were very focused on. So more broadly, just thinking about what this process looks like, there's a sort of very simple outline of the supply chain at the top of that slide, and we're really focused on that light blue box, the hospital blood bank. That's who I was working with. And they're making these two kind of key decisions: replenishment, how much they order from a regional blood center that will sort of be collecting, processing these units, and then make an order typically once a day. It's more in some places. And then an issuing decision, like when a doctor says that they need blood for their patient, the hospital doesn't sort of choose which of these units that we've got in stock do we issue to meet that need. And when making these replenishment orders, particularly, you've really got to balance wastage and shortage. Shortages can put patients at risk if you don't have the blood available to treat them. Then there's a financial side to wastage. It costs money to collect and process and distribute these components, but there are also moral implications to wastage, because you are, not making the best use of this altruistically donated product. And I think that's something that the sort of blood supply chain, the people that you talk to at NHS Blood and Transplant, really care about. You often in the literature see very high wastage rates for platelets, sort of up to 10 to 20%. And this is because they've got a very short useful life, sort of at most 3 to 5 days when they arrive at the hospital, depending on exactly which country you're in and how they've been treated. And blood in general and platelets specifically are quite widely studied examples of perishable inventory problems where you do have this short life, this shelf life to contend with. You can't just hold your stock for as long as you like. You really got to worry about it being wasted. So the first of the sort of two sections I want to talk about is called faster optimization. I'm going to start by explaining why, in the setting of trying to find the replenishment policy, finding the optimal policy is really hard. So we're focused here on this left-hand side of that schematic supply chain I showed you, the replenishment, how much should we order each day from our supplier. And the way that we're modeling this is with a Markov decision process. So a Markov decision process is a method for modeling sequential decision-making problems, where the choice that you make now will affect what you see in the future, potentially over multiple steps. So the best action at the moment is not necessarily the one that results in the best immediate effect. It's the one that does best over multiple steps. In this circumstance, you can think of the fact that the units I order today may well be in stock for multiple days. And if you're thinking about this particularly from a reinforcement learning perspective, which is where this gets used in machine learning, the concept here is an agent looking at the state of its world, choosing an action to take, seeing how that affects its environment, seeing its state being updated, getting some reward signal about how good that action was, and then repeating that process in a loop. And the essential elements of this are, what are the states our world can be in? What are the actions we're able to take? What's the function of that reward? What signal do we get depending on what's going on in the environment? How do the states transition? And then maybe a discount factor to account for the fact that future rewards, just like, there's a time value to money, future rewards may be less valuable than present rewards. And in general, the goal is to maximize the expected future reward and really to learn a policy, which is a function that's going to tell you what action to take in a certain state that maximizes that expected future reward. So thinking about how we use this to model the platelet inventory problem, well, the states are the number of units of platelets we've got in stock by how old they are, and the number in transit, if there are some in transit. The action is our replenishment order quantity. The reward is the cost of operations times -1, and that would include things like a variable order cost, a fixed order cost, and then sort of proxy costs for the effect of wastage and shortage, for example, because it's quite hard to put cash costs on the effect of a patient being put at risk or the moral implication of wastage, but there are people in the literature who put proxy costs on those that you can include. And in this case, maximizing the future reward means minimizing that future cost of operations. So generally speaking, both in the literature and in real life, people are using approximate policies. So on the left-hand side, it's really common, certainly was the case at UCLH, to use these heuristic policies with a small number of parameters, things like just making a fixed order every day, a base stock policy, an SS policy. The sort of little tree diagram is my schematic of an SS policy. So basically you look and say, is the total number of units I've got in stock less than little s? If it is, I'm going to order up to big S by placing an order that's big S minus I. If not, then I won't place an order. I think I've got enough in stock. Often these parameters are set using practitioner knowledge, but certainly in the research, you'll see people fitting these parameters using stochastic mixed integer linear programming, using simulation optimization. Another option is sort of arbitrarily complicated policies, arbitrarily complex policies. So not really going to talk about it very much today, but as part of my PhD, I did look at how we could use deep reinforcement learning to learn these policies where you have a neural network that's doing that job of saying, given what state you're in, what action should you take? Those can be, much more complicated, but also harder to learn. But what about the optimal policy? This is a Markov decision process. So for that representation of the problem, we can, in theory, use value iteration, which is a dynamic programming algorithm, to find the optimal policy. I'm not going to go into detail of the algorithm. It's there in a box on the left, but the problem with this is it involves multiple nested loops. So over multiple iterations until convergence, you've got to loop over all the states, all the actions, all the states. And so the time required to do value iteration scales with the number of states you've got squared times the number of actions. So that's already not great scaling. For perishable inventory, we've then got to contend with the fact that the state space grows exponentially with the maximum useful life of the product. So on the right-hand side, if we've got a maximum useful life of m and a maximum stock holding per age of n, you can see that our number of states grows exponentially with that maximum useful life m. There's some sort of illustrations below it to show what that would look like. So if our number of states is growing exponentially with our maximum useful life, and then that's then being factored into our scaling for value iteration, you can see this can quite quickly get out of hand, sort of our curse of dimensionality when we're dealing with these sort of exact iterative methods. So when is finding the optimal policy feasible? So Namias wrote a really nice review of perishable inventory in 1982, and at the time, sort of on that's the quote on the sort of left there, he was saying that, this takes quite a long time if the maximum useful life is greater than or equal to 3. So this is really impractical for real problems, trying to compute this optimal policy. On the bottom there is an extract from a paper that was in EJA a couple of years ago that kind of came out while I was doing my, I was sort of in the process of doing my PhD. And they were saying for the problem that they were looking at, when the maximum useful life was 3, 4, or 5, that was too large. They couldn't compute the optimal policy numerically using something like value iteration. I think sort of the observation we had as a group was that there's 40 years between these two, and they're making quite a similar observation. And computers have changed quite a lot over 40 years. So was there something we could do here? And what we landed on was using GPUs and a piece of software called JAX to make use of them, which is what I'll talk about now. So GPUs are built for parallel processing. They were originally developed for sort of gaming and graphics. And the key sort of thing that was required there is to be able to compute the same operation on multiple inputs at the same time very quickly. So your sort of standard CPU on the left there with 12 cores, the GPU to its right having certainly hundreds, often thousands of cores. Now they're individually less powerful and they're sort of much more constrained in what they can do, but what they are really great at is processing that same operation lots and lots of times on different inputs. And this has been absolutely fundamental to developments in machine learning and AI over, let's say, the last 10 years. Alongside sort of the increased availability of data, I think the fact that people have been making use of GPUs to train their neural networks has been transformative. Is why we have LLMs and large LLMs and all sorts of other very exciting developments. But the problem is they're quite, or certainly they were until relatively recently, it's quite hard to use GPUs to do your own custom things. So there's been a lot of development of software and machine learning to make it easier to use them. And so JAX is, I've described here, an accessible way into GPU programming. It's open source software. It was developed in part by Google, and is really developed to support machine learning workloads. But what it lets you do is take advantage of GPUs and all that really exciting parallel processing power, the ability to run lots of things at the same time, without needing a sort of deep knowledge of the hardware. Whereas previously, I think if you wanted to do things that were not completely routine, you needed a deep knowledge of the hardware to really get the gains of the GPUs and code it properly. And that's just very niche knowledge that not a lot of research teams will have access to. So I think it was very hard for a lot of people to really get the benefits of GPUs for non-conventional workloads. So what did we do with this? Well, we sped up dynamic programming to solve larger problems, which I'll talk about now. So the idea here was we wanted to use parallel GPU implementations of value iteration for getting that exact policy, and also simulation optimization for fitting some heuristic policies. To find the optimal policy for problem instances from the recent perishable inventory literature, where they'd said settings that they were interested in were infeasible or impractical, and then compare the results to some heuristic policies with parameters fit using simulation optimization. And the goal here, particularly, was that we really wanted this to be accessible. So we're bringing JAX in because we wanted to require minimal specialist knowledge of GPU programming, something that sort of, I think JAX is something that most research teams who currently work in Python particularly could learn quite quickly. And we wanted it to be feasible on freely available or affordable hardware. So all the work here, except for one slide, which I'll explain when we come to it, was done on a GPU that I bought for £400 and it lives under my desk. And a lot of this can be run on GPUs that are freely available in the cloud. And the sort of the idea here was that it's great if we can find the optimal policy for those large problem instances. That's a sort of useful end in and of itself. But it also helps us to investigate the scaling property of other approaches. There will remain problems that are sort of out of reach. This isn't a complete magic bullet. It pushes back, pushes forward, pushes against the frontier, so we can solve bigger problems, but we're still going to need heuristic solutions for some much bigger problems. But getting the optimal policy really helps us understand how those heuristics scale as problems get bigger, and therefore which the most appropriate ones might be. So thinking about why JAX and GPUs are a good fit for these methods. So JAX makes it really straightforward to write a simple function and run it on many inputs in parallel at the same time on a GPU. And it also has a really nice capability to compile code in a sort of just-in-time way, sort of when it's needed to speed up repeated operations. And these are both things that are ideal for value iteration and simulation optimization. The state updates for value iteration, the simulation rollouts and simulation optimization. Those are all independent, so they can run in parallel. And in both cases, we need multiple iterations or multiple generations to get convergence. And so if we spend a bit of time doing that compilation up front, we then save a lot of time as we repeat those operations multiple times until those algorithms have finished. So we found the optimal solutions for some big problems. So this is sort of a sort of summary results slide. There's 3 papers on the left-hand side. They all included problem features that were relevant to the work we were doing around blood inventory. The Mir-Jalali one, scenario C, was very specifically a platelet inventory problem set in Canada. So the blue dots, we've got maximum useful life is the grid there going from 2 to 8. The blue dots are the size of the problems that the original authors said they were able to complete. The ticks are where there was a scenario they were interested in, but they said, oh, it's too big. We can't solve it optimally. Can't solve it exactly. We're going to use some approximate methods. The red cross is the Mir-Jalali maximum useful life equals 8 case that had 12.8 billion states. All those states did not fit into memory on my computer. So that's an example of where, this is not a sort of magic bullet. There remain things that will be still requiring approximate and heuristic approaches. But for all those problems, we've really pushed forward the scale of problems that were feasible. And I think particularly for the Mir-Jalali one, that M equals 5 case is the realistic platelet case in Canada. They do have a maximum useful life of 5. So the fact that you can't do 8, which is completely hypothetical, is not necessarily a big problem. Some indicative speed, and I've said indicative here because we weren't running, the exact same code these researchers ran on the exact same hardware. But if you were reading one of their papers and thinking, oh, that seems like quite a long time, what we found for value iteration is that a problem with substitution was reported to take 80 hours in a MATLAB-based approach in the original paper. It runs in 2 minutes, so 2,000 times faster using this approach on a GPU. And there was a previous attempt to implement this, or successful attempt to implement this on GPU by Ortega in 2019. They used CUDA, which is much harder to work with, needs a lot more expertise. And our approach is running 6 times faster than that in terms of their reported time. Now, part of that will be due to the hardware issues. So the thing I really wanted to highlight here is it's not that by using this, JAX is more accessible way of doing it, that you're necessarily getting lower performance. Absolute top of their field experts in GPU programming will probably eke out some extra performance by writing things at a lower level. But for most normal people, using this approach is going to get you really good results with the GPU because the way that the code is mapped is very good. The way that JAX takes your simple code and turns it into code that runs really well on GPUs works effectively, which is what that second twin is showing. In terms of simulation optimization, just as a quick comparison, so my approach, we were able to run 50 sets of heuristic policy parameters on 4,000 simulated years each in under 15 seconds. And looking at the sort of total time for convergence of these algorithms, the total time to fit the policy could run between 2 seconds and 16 minutes, depending on the size of the problem. One of the really nice things about JAX is this easily scales to multiple GPUs. So with exactly the same code, you can just run it on somewhere with bigger chips and get better results. So we had a problem with substitution with almost 17 million states. The original authors said they couldn't complete value iteration on this in a week with a MATLAB CPU implementation. So using JAX and the GPU that was £400 and is under my desk, that ran in 3.5 hours, which is the biggest bar on the left there. Being at university, you can sometimes have access to some high performance chips. So running that same code on 4 data center GPUs, that was less than 30 minutes with no code changes, just needed to run it in a different environment. And just looking at how the simulation optimization policies compared. So x-axis here being how long did it take to find the optimal policy, and y-axis being what was the gap between the optimal policy and the heuristic policy. So the biggest gap was 2.5%. In general, the smaller problems had a larger optimality gap. And fitting the heuristic was much, much faster. I think the longest heuristic took about 1,000 seconds, whereas you can see that the longest optimal policies took well over 100,000 there. So the takeaways from this section is really this idea that software from the machine learning communities, in this case, particularly JAX, can really help OR researchers take advantage of GPU hardware to accelerate methods that are of interest, like value iteration, dynamic programming, and simulation optimization. If we can run our optimization algorithms faster, then we can compute the optimal policy for much larger, more realistic problems. I think there's lots of problems that can be framed as a Markov decision process, and this can also be applied to other optimization methods. And I turned my research code into a sort of accessible Python library called MDPax, which is now available on GitHub. So if other people are interested in applying this to their own MDPs, hopefully that will give them a quick start. So the next section I'm going to talk about is going the other way around. So how do we bring ideas from OR into ML? How can ML benefit from those ideas? I'm going to start by talking about an idea for a machine learning-based platelet issuing policy. So we're now on the right-hand side of the supply chain, looking at the other side. So a doctor's asking for blood for their patient, and the hospital blood bank has got to decide which unit of the ones they've got in stock should they give them. So the standard practice here is to issue the oldest unit, follow an oldest unit first out policy. So if all the platelet units that you're asked for get transfused, then that's optimal. They'll go out, they'll get transfused, they'll be used, you'll be getting rid of the ones that are about to expire. What we found talking to UCLH, our partner hospital, was about 8 to 10% of the time, the units would go out to a ward, and for whatever reason, they wouldn't be transfused to a patient. Now, if that happens on the last day of useful life for that unit, it's going to be wasted. But what we found is if younger units were issued by chance, or because they just happened that the stock at the time was relatively fresh, they were generally kept in such a state that they could come back to the blood bank and were fit to be issued to a new patient if they came back before expiry. So what we proposed, and named by my supervisor Martin Utley as youngest unit for predicted returns, was a new issuing policy based on a predictive model. So the idea here is that the request comes in based on the characteristics of the patient for whom the blood is being predicted for, and some other statistics like how far in advance, not statistics, some other features like how far in advance is that request being made, what time of day it is, things like that. The model predicts, is it likely this unit is going to be transfused or returned? If it predicts it's going to be transfused, we just issue the oldest unit. That's great. That will be used up, it won't expire. If we predict it's going to be returned, we instead issue the freshest, youngest unit, because that way there is time for it to go out, not be used, come back to the blood bank, and be issued to someone else and still get used rather than expiring. Now, the way we approached this was relatively unusual. And this is sort of really where this OR coming to ML comes in. And so this is the idea of a simulation at first approach to evaluating predictive models. So a typical ML process in academia, you start with this very variable step, which is very challenging in healthcare, but probably easier in some other domains, of gaining access and permissions to data. Then you'll move through model development and training, evaluating your model. Here, I'm assuming it's a classification model, so using classification metrics, but that could be regression. And then hopefully you publish it and maybe you deploy it, although I think that's still relatively unusual for models developed in academia. So can we build simulation into the process? Because the way we're evaluating those models with classification metrics, it tells us how good the predictions are, but it doesn't really tell us how useful the model is. Often that model is going to be embedded in some wider workflow, and there's not a direct relationship between how good the predictions are and what that means in terms of KPIs, in our case, things like wastage and shortage. So one approach that's become reasonably common, I've seen quite a few papers covering it, is to simulate after the predictive model is trained. So in that top workflow there, inserting that orange box after evaluation using classification metrics and saying, okay, now we're going to run this model in a simulation of the workflow and see, with this model that we've already trained, how does it affect our KPIs? And then maybe, again, that leads to publication and deployment. What we proposed here, and this is really inspired by Gina Dumkruger's PhD she did at the University of Arizona, where she'd looked at sort of also blood inventory and how the varying quality of demand forecasts affected the results, is to say, well, let's start by simulating the deployment of a model using simulated predictions from a machine learning model and work out how good does the predictive model need to be in order to improve our KPIs. Then if that looks promising, then we can go and gain access and permission to our data, do our model development and training, do the classical evaluation. And then at the end, we can reuse the simulator that we have to see, well, now that we've trained this model, is it good enough to improve those KPIs? But the key step is using that simulation right at the very beginning to see, is this a model that's worth building? The benefits of this approach, it's an early sense check on potential utility. It forces you to develop a solid understanding of the workflow you ultimately want to use your predictive model in at the start of the project. You can reuse that simulator at multiple points throughout the study rather than just once. You can start work with higher level, less sensitive data that should be easier to get access to. So you're sort of really removing one of those blockers on getting started with work. And certainly in healthcare, what we often found is that, the people who are responsible for approving projects, pulling data from confidential systems, etc., their time is very much in demand. And so we think, this is a way that you could quite quickly demonstrate potential utility and hopefully raise the priority of your project, help support funding applications, etc. And so this is probably most likely to be useful in situations where there are, barriers to starting the traditional model development and where you really understand the workflow well, and so you're able to build that simulator quickly. So I'll just talk quickly about how we applied that to the platelet issuing problem. So I won't go through this in huge amounts of detail because I probably stuffed too much into this presentation. But this is my simulation of the blood bank workflow for this particular part of the project. And so the numbered steps are going through a sort of loop through every day. So there's a routine order placed in the morning, which is our replenishment order that we talked about in the previous section. Then the second part, we're going to fill demand that arises in the morning from the hospital wards following our issuing policy. At midday, the units that we issued yesterday that didn't get transfused come back in. So they're now available to fill demand that arises in the afternoon, as well as whatever else we had in stock. And then at the end of the day, the stock gets aged, we dispose of expired units, we calculate the reward, the costs that we've incurred during the day, and we loop back round to place another order the next morning. So the key step of the simulation first approach is being able to simulate predictions from a machine learning model so that you can explore how the quality of that model would affect your KPIs. So here we're looking at a binary classification problem for a given request for units. Will that unit be returned or will it be transfused? And because it's a binary classification problem, we're going to look at two metrics, sensitivity and specificity. So normally what you do is you would train a model and then look at how that model did in terms of sensitivity and specificity on some real data. Instead, in order to simulate these predictions, we're going to set those values and simulate the predictions you would have seen if you had a model that had a sensitivity and specificity that good. So if we follow through the diagram on the left-hand side, we'll have some probability underlying that units will be returned or transfused, and we use that to assign the true label, what's actually going to happen in our simulation for that particular request. And then for the returned ones, we're going to sample what label to give them based on the sensitivity, because sensitivity tells us the probability that we say that a unit was returned, given that we said it was. For the transfused, for the things that will actually be transfused, we're going to sample their label based on the specificity, because the specificity tells us what's the probability that one was transfused, given that we said it was transfused. Based on those simulated labels, that then decides what happens in terms of what unit gets issued in the simulation. And the key idea here is that you look over a range of different values of sensitivity and specificity, simulating predictions from a range of different possible model quality, range of models of different sort of simulated quality. And so to try and make that a little bit clearer, so these are some plots showing how KPIs, in this case service level and wastage, varied with the predictive model quality. So the axes here are the axes you'd have on a receiver operating characteristic plot. So sensitivity there is on the y-axis, and 1 minus specificity is on the x-axis. So here, a perfect predictive model would be up in that top left-hand corner. And what we can see here And so the contours are basically showing the values that you get of those KPIs when you simulate a model with a sensitivity at the value on the y-axis and a 1 minus specificity on the value on the x-axis. And what we can see is that as our model improves, goes up towards that top left-hand corner, wastage decreases, service level stays about the same, and there are usefully combinations of model performance above that line showing the oldest unit first out policy, which is the conventional policy, that get lower wastage than that. So what that tells us is that there are combinations of predictive performance that would get us better than oldest unit first out. If that oldest unit first out was way higher, we'd say we can't beat it. But what we are seeing is there are lower values of wastage above and to the left of that contour. So a sufficiently good predictive model can cut wastage while maintaining service level. And what we saw in some sensitivity analysis that the impact was greater when the return rate was higher and when the stock was generally older on arrival. So because this looked promising from our simulation first, we did then get permission to go and get the full data and train a model. And so here I've overlaid that sort of thick black contour as the receiver operating characteristic of the actual model we trained, sort of over these simulations of what you would see in terms of wastage. And so again, that actual model line is above that OUFO contour for parts of it. So you would be able to select a threshold for this model for deciding what was returned and transfused that does better than the oldest unit first out policy. The left-hand side is just using inputs from UCLH, where wastage is actually, although it's something they're concerned about, quite low. The right-hand side is if you look instead at replacing the distribution of useful life on arrival with one from a US hospital where there was a shorter useful life and the stock was older on arrival. And you can see there that the wastage values are much higher, and that if you're able to improve this first model we built and push that up towards the top left-hand corner, you could get some really significant reductions in wastage. So takeaways from this section, by simulating machine learning models of different predictive quality, you can understand how the KPIs vary depending on how good the model is. It's really trying to bring an OR perspective of workflow simulation to focus, like we should be developing predictive models based on where they're most likely to be useful, not just places where we can get good predictions. Those predictions have got to be useful within some workflow. We think this approach is particularly useful in settings where there are really significant barriers to starting model development, so you can demonstrate why this would be a good model to develop and why it's worth sort of breaking through those barriers. And the really important point is that if a near perfect predictive model wouldn't improve your KPIs, then just don't bother trying to build one. Like, don't try and go through those barriers, move on to a different project. So just to quickly wrap up, this has been a whistle-stop tour of 2 examples of the benefits of being aware of developments and practices from neighboring fields. And it came out of my PhD project was really focused on a single UK hospital site trying to do platelet inventory management. So taking advantage of computational tools from ML can help speed up OR methods and make larger problems more tractable. And adopting an OR workflow perspective, like at a really early stage in machine learning projects, when you're considering, well, what should we be predicting here? What's going to help? Can help to focus those efforts on predictive models that should be useful in practice. There are papers and a preprint covering this work. There's also my Python library MD packs that I mentioned earlier. So those are all linked from my homepage, and that QR code should take you to my homepage. And yeah, just some quick acknowledgements. So my supervisors were great. So Ken Lee, Wai Kyung, Martin Nutley is on the call and was a real rock during this, and has also helped me with these slides. And just a really big thank you to the UCLH team, because they were invaluable in terms of both getting data and also just understanding what their challenges and concerns were, and how this, how these workflows all fit together and what's important. Yep. So very happy to take your questions, and thanks very much for joining today.
Thank you very much, Joe, for very exciting presentation of this piece of research for which you were awarded. We'll accept questions either in person. Carol will take questions from Newcastle, and I will be happy to take questions from the Q&A section of Zoom. And Colette Fletcher, who is our executive director, will serve as an additional pair of eyes to highlight any missed questions. So I understand that there are questions in the audience, if you want to start with them.
Hi, Joe, can you hear me?
Yes, I can. Hi.
Thanks for the presentation. So I have two questions with regard to your two, let's say, parts of your presentation. So starting with the first one,
Yes.
what types of problems can you solve with your method, and how do you call solvers within every iteration of simulation? I mean, which solvers can you utilize with GPUs?
Yeah, great question. So this was like my work was specifically focused on sort of dynamic programming, and then a little bit of simulation optimization where we were we would do the simulation on GPU, but then we would use a CPU-based solver. So I think for this particular piece, we used NSGA2, which, although it's sort of multi-objective, actually just worked quite well with the inputs that we had. So for simulation optimization, it was do the meat of the work on GPU, run those simulations there, and then just feed the results back to a CPU solver. I think there is some work on GPU-based solvers as well. I mean, I think one of the really interesting things that I did have a slide on is that NVIDIA at the end of last year released, I might have it actually. Yeah, this QOpt, which is their library for using GPUs to run linear programming, mixed integer linear programming. Yeah, so I was quite focused on dynamic programming and just running the simulations rollouts rather than the optimization. But I think this is definitely spreading more widely to different types of workloads. Does that help?
Yeah, thank you so much. So still the CPU is bottleneck in your study if the problem set every particular, let's say, decision iteration if is hard to solve, then yours will be slowing down, right? So that's why I understand the bottleneck. Okay, thank you. And second question is, how do you evaluate the false positives and false negatives, considering your simulation might end up with a state that has never been observed before? Like, how do you know? How do you compare with the real data? I couldn't get that part, maybe.
Yeah. So I think we like the focus. Like, I think we just sort of focus on using sensible inputs in UCLH and looking at, when we set the things, did the wastage rates line up when we used an oldest unit first out policy? But I think if you were to do this to deploy, you would probably focus a lot more heavily on a specific situation, like on a specific. Let me go back. We used specific inputs from UCLH and looked and checked that things looked sensible in terms of KPIs. But I think you're right. I think there is that, this exercise, because it was about trying to demonstrate whether there was a reason to go and build the model, probably would have benefited from some more, rigorous simulation validation to check, that everything completely lined up with reality if we were going to go and deploy it. It was just kind of focused on, do the KPIs look sensible given what we see in the hospital?
Okay, are there any questions from the room, please? We have a question.
Yeah, we have
here.
Sorry, one second.
Okay.
Thank you very much for your excellent presentation. I'm an academic member of staff from Newcastle University. So I'm currently supervising a PhD student who is also applying reinforcement learning in inventory management. So may I ask, how can my students, maybe perhaps the other future students who are working on reinforcement learning to access your dissertation? And you have mentioned that you published the code on GitHub, so that's really helpful. So I just wonder, how can they access your full dissertation?
So it is on the UCL Research Papers service. I can't remember if I've added it to my homepage yet, but if I haven't, I'll add it there. And it's so joefarrington.github.io. I'll make sure there's a link if there isn't already. Thanks.
Okay. Are there any more questions in the room, please?
Thanks, Annie.
Yes, sorry?
Oh, so I was just saying there's no more in the room.
Questions. There are some questions in the Q&A part related. First is, has this yet been implemented in practice at UCL? If so, to what effect?
Yeah, I would like. So the reason I chose this project originally was because it seemed like there was a really strong path to implementation. Because I think so. My program was AI for healthcare, which was sort of pretty broad. A lot of those things did involve things for patients. I was like, oh, this is operations. There should be far fewer moral and ethical barriers to getting this implemented. I think COVID did a lot of disruption to the plans to join various data systems together. So in order to get this running, we would have needed the transfusion laboratory system to talk to the electronic health record in a research environment. And we didn't get there before I needed to hand my thesis in. So there was a plan to try and use the idea of issuing fresher units or the youngest unit for predicted returns using staff's predictions based on what they have observed of certain doctors doing or certain units doing. But I haven't spoken to them really recently to see if what that looked like. They were going to try and do it without the predictive model because the predictive model was hard to get running without connecting various pieces together. So I think this is probably something that most people on the call are familiar with. Like even when you've got access to the data, actually making sure that all that data is accessible live to deploy something on a relatively constrained time frame is challenging. So yeah, sadly not yet.
Okay, thank you. And there is a question from Christos Vasilakis.
Oh,
Great
hi,
research, Joe. Many congratulations. May I ask whether implementation of the tool algorithm has been discussed with hospital collaborator? That's okay, you answered. And if yes, what are the main challenges? Maybe you can now focus on what you see as main challenges.
Yeah, absolutely. So I think there was a huge amount of enthusiasm. I think the reason why we were doing the project there is because they were really interested in how we could use data, operational research methods, machine learning methods to help support them. I think the biggest challenge was the hospital has lots of different IT systems and they talk to each other via FHIR and other interchanges for day-to-day things, but trying to pull all that data for research consistently in one place that PhD students allowed to access was just turned out to be. They might have fixed it by now. I think Zella's on the call. She might know if they've got there. It was to do something like this that requires knowing the inventory and what's going on with the patients and things like their latest platelet counts and sort of where they are in the hospital and what's planned for them just requires bringing data together in real time in a way that wasn't feasible. So I think that was the big challenge.
Okay. And we have a question for Gilberto Lusso. What was the feedback from the hospital staff?
Yeah, so I think the first thing that they were really interested in was the fact that there were sort of putting some numbers on these returns. Because I think, they did a huge amount around wastage and looking, but hadn't necessarily followed it through the way that I had. Like they suggested this was a thing they knew, but they hadn't really quantified it. So I think they were really interested in that. I think they were the consultant who leads the lab was really interested in the idea. I think thought it was really cool conceptually, and then was interested when we were able to show that, yeah, in a simulation, this looks promising. There aren't other bottlenecks that would stop the model from being useful, and that we could train a model that was reasonably good. So yeah, I think they were really interested. She was really keen that they tried it out, like I say, using staff judgment to see if that would help. So yeah, I think, I mean, they were great collaborators. I was really lucky.
Thank you. I have one question for you, Joe. I have to admit, I can't see how I can write it in Q&A.
Oh,
so I
okay,
will just use the question. In your data set that you showed in the second part of your research, is the data set balanced or not? Because I guess it affects the measures that you use to evaluate the accuracy of prediction.
Yeah, absolutely. So no, it wasn't balanced. It's probably about 10% of the time, 8 to 10% of the time that the units get returned. So that is the reason for looking, I guess, at the receiver operating characteristic and sort of trying to pick a threshold. So these, I didn't go into it because I put too much in my presentation, as I often do. But the idea is these stars were based on the training data and the simulation results of how the threshold affected the wastage, like how the sensitivity specificity trade-off where you decide, should we predict this to be returned or transfused, was based on the training set. Those were the best thresholds, and then this is how they show up on the test set. So like you say, sort of acknowledging there is this imbalance and saying, well, given that we don't we'd like good classification performance, we want to choose our threshold to do well on reducing wastage. That's where we set it, rather than saying, oh, it should be 50-50, because there is, as you say, that balance.
Thank you. We have one more question. How accurate is the demand forecasting that drives all of this? I would expect demand variability and seasonality.
Yeah, absolutely. So we didn't do any explicit demand forecasting. So this is based on like when we were learning replenishment policies, it was by based on distributions of demand, but there's no explicit demand forecasting step in this. But there's a lot of seasonality. Mainly day of the week was the big seasonal factor that we saw. There is some analysis in the appendix of my PhD looking at it on the basis of months and years and various other things. But weekdays were the big factor there, which is why weekday also like factors into the state, which I possibly didn't mention. But you will often find that you need a different, if you've got that varying weekday demand, you will be making a different decision with a certain stock on a Friday than you would be making on a Monday. So yeah, it's great. Let's pick that up.
Okay. Thank you very much, Joe, for a very exciting presentation. And let's give Joe a round of applause, please, virtually and in person.
No, thanks very much for having me. I really appreciate the opportunity to talk.
Okay. Now we'll move to the Beale winner presentation. The Beale Medal is the Society's most prestigious award and is given in recognition of an individual's sustained contribution over many years to the theory and practice of ORR in the UK. And the winner of the 2025 Beale Medal is Professor Stewart Robinson. Stewart holds an honors degree in management science, operational research, awarded in 1985, and a PhD in management science, awarded in 1998, both from Lancaster University. He is a fellow and former president of the Operational Research Society. He served this role in the period 2014 and 2015, and I was very lucky to be a vice president at that period of time of the society. And he's also chair of the Chartered Association of Business Schools. Stewart started his career as a business analyst for a shoe retailing company, and then as a consultant with ISTEL, now it's Royal Haskoning DHV. And during this time, he gained experience in performing and supporting simulation studies with a wide range of organizations. In 1992, Stewart moved to Aston Business School, where he lectured in operations and information management. He spent there 13 years. He spent 13 years then at Warwick Business School, and he was awarded a title Professor of Operational Research in 25. He held various roles during his time at Warwick, including Director of the Executive MBA program, Associate Dean for Specialist Master's programs, and Head of the Operational Research and Management Science Group. Stewart joined Loughborough University in 2011 as a Professor of Management Science and had the role of Associate Dean for Research, then subsequently becoming Dean of the School of Business and Economics in 2015. In July 2022, he joined Newcastle University Business School as Dean and Professor of Operational Research, where he is now. Stewart's research interests are in the practice and use of simulation models. He has published 7 books and over 200 refereed journal and conference articles, making contributions to our understanding and the practice of conceptual modeling, model validation, output analysis, participatory modeling, behavioral operational research, and comparison of simulation methods. Stewart is co-founder of the UK Oral Society Simulation Workshop Conference Series and the Journal of Simulation. The title of Stewart's Beale Lecture, which he is giving in person now at Newcastle University, is How We Develop Models, reflecting on 40 years, nearly, of modeling. Over to you, please, Stewart.
Thank you, Sanya. Can I just check, can you hear me online?
Yes.
Yes, excellent, good. And you can see the slides? I'm assuming that's a yes. So, anyway, thank you very much, Sanya, for the introduction, and thank you also to Joe for his excellent presentation, which is a real example of OR in use. And great to see the work that Joe has done. So thank you for the opportunity to give this lecture. Welcome to those in the room who've turned up today, and welcome to those online. When I was thinking about this lecture, I realised there may be a range of interests that are coming into the room today. So definitely trying to avoid a technical presentation. I hope to entertain you a little bit as well with a few stories, but also to get across some key messages about what I've learned about modelling over the years. So just to give you a quick overview of what I intend to do, I'm going to start with a quick introduction to simulation. Joe actually told you a bit about it, but we'll have a very quick introduction because that is my main field. And some of you, well, it's helpful for us all to be on the same playing field when we start talking about that. And then I'm going to say a little bit about how I started out in my career in simulation modelling, a bit of theory about how we develop models. And what I really then want to pull out is 5 key lessons about how we develop models that I just spent some time reflecting on when I was thinking about the modelling that I've done over nearly 40 years. More on that in a moment. And I will finish off with an interesting topic called Do Not Believe Your Own Propositions when we get to the end. Just want to also say welcome to the N8 Operations and Supply Chain Management Research Seminar Series. My colleague here, Jing Singh, who actually just asked a question, is leading that from Newcastle's point of view. This is for the research-intensive universities in the north, and is a series of seminars. And when Jin-Sin said, would you give one? I said, well, I'm doing the Beale Lecture. Why don't we combine the two together rather than me speak twice, probably saying the same thing over? So welcome to that group as well. I know we have some of that group in the room too. Right, so let me just start with an introduction to simulation. I have two apologies about this introduction. It's a video. The first apology is it's a YouTube video, which means you're going to get an advert. I have no idea what that advert's going to be. What I would point out is I'm not logged in on my own account, so it has nothing to do with me whatsoever, whatever random advert we get. The second thing is that the actual video is an advert for a particular piece of simulation software. I want to make clear, as the BBC always does, that other software products exist. But I thought it was a very good way of getting across to you in literally 90 seconds what on earth it is that I'm talking about, and I've spent nearly 40 years doing. So let's see if this works. One thing that's always dangerous is flipping into the internet at this point.
How do you turn AI complexity into business growth? This is where the new ITIL comes in, the common language that drives growth across the organization with clarity and speed. AI native by design for IT service management, and now expanding for every role.
What is AnyLogic? How do you remove bottlenecks in a production facility? How do you better plan a rail yard? How do you assess possible passenger traffic in an airport area? How do you optimize warehouse operations? Experimenting in real life can be just too risky or too costly, or maybe not possible at all. Try modeling anything close to a real system in Excel, and the sheets and formulas will quickly become too complicated and unmanageable. Simulation modeling with AnyLogic is a better solution. Build an interactive simulation of your business. It's like a video game where you can test changes at any level of detail, communicate ideas through dynamic animation, and collect statistics. A simulation model is a risk-free environment, less expensive than real-life experiments, and much more flexible and intuitive than formula-based Excel models. AnyLogic has built-in industry-specific modeling toolkits, which speed up simulation of any complexity and scale. That's why AnyLogic has become the #1 simulation tool in logistics, manufacturing, mining, oil and gas, healthcare, rail, and other industries. The software's experiment framework allows you to run complex experiments, including those for training AI algorithms. AnyLogic Cloud takes these and other software abilities online so you can easily share your insights and collaborate on ideas. Join industry leaders from around the world and start building simulations today for free with AnyLogic Personal Learning Edition.
So, as I promised, an advert for AnyLogic, but as I say, many other simulation tools exist. But I hope that gives you a general sense of the type of approach that I've been working with for all these years, and very much focused on the idea of looking at business operations and how we improve those operations. So just to give a little more formal definition around simulation modeling, this would be how I would explain it. Basically, it's an experimental approach. So we're not looking here at straight optimization of a problem. We're looking at actually creating an imitation, simplified imitation of a system on a computer using software in most cases, such as AnyLogic we've just seen. And what we're doing is modeling that system as it progresses through time. And what we're aiming to do with that is to better understand that system, but also to look at ways of improving that system, deliberately using the word improving rather than optimization in this case, albeit that we can do work that helps us move towards an optimization. It's an experimental approach. So looking at the diagram I have there, we have the simulation model, the blue box. We have a set of inputs that drive that simulation, which describe how the system is set up. It generates a set of outputs, which are statistics about how that system is performing. And based on what we learn, we then go through a loop of experimenting, changing the inputs, and seeing if, when we rerun the model, that leads to an improvement in the outputs. And my career really has focused on using this in the types of operations we just saw in the video, So anything from warehouses, manufacturing systems, health systems, service systems, etc., are the sort of systems that we look at using the approach. I've never really specifically focused on one type of system. My interest has very much been in how we use simulations across a whole range of contexts. So, nearly 40 years of simulation. My clicker stopped, there we go. So in the beginning, actually the beginning of my simulation career, sadly I can remember the date, was October the 27th, 1986. And that was the day that I joined a company called Istel, which Sanya mentioned, which at the time was part of the Rover Group and had previous life been the British Leyland Systems Company, and had recently, in fact, separated out and was starting to deliver work to companies outside of the Rover Group. It was effectively the subset I was in was the operational research group of Rover originally. I previously learnt actually a bit about simulation at university when I was an undergraduate, and I had previously been working for a shoe retailing company, but more doing straight analysis, not really doing modelling. So to me, very much, when I took up modelling, and particularly simulation modelling, was on this date. Now, I thought we need a little bit of audience participation. Don't worry, I'm not going to get you up and do anything. I'm aware we have a lot of people online, but this is your chance to answer a question. I was looking back at what happened on the 27th of October, 1986, and chose not to mention the fact it was the day of the Big Bang. That doesn't mean I'm that old, at the beginning of the universe, but the Big Bang was actually the day, for those who are old enough to remember, when the financial markets were deregulated. I hadn't realised it was the 27th of October, 1986. Anyway, that's a bit boring to think about. So there was also a significant event on British TV on that day. So your quiz question, which has a prize, is to find out and tell me what major British event, or what major British TV event happened on Monday the 27th of October 1986. And the prize, if you send your answer to my email address, first person to get it, will get a free copy of the new edition of my book. This is a way of me also advertising the new edition of my book, which literally I got last week. So it's really hot off the press. Now, there is one rule here. I can see some of you already looking at your phones in the room. If you answer before I finish speaking, you are disqualified. That means you're not listening to me. So after I finish speaking, please feel free to answer. I will put the answer up on LinkedIn once I've had some valid answers come through. And I will even promise to sign the book should you win. Right, so where did it all start? What was it like in 1986? Well, Istel, the company I joined, developed one of the first what was described as visual interactive simulation software tools called CY. So see the system and understand why it's behaving as it is. And this was the type of computer that we were working on. In fact, it's two computers. The one on the right did the processing, the one on the left drove the graphics. They were fairly basic computers with not a lot of memory on them. Now, for those who get really excited at this point and think I'm going to start talking about punch cards, because that's what we like to do when we're getting old and talk about how bad our computers were, I just missed punch cards by about 2 or 3 years. So I'm sorry, I'm not going to talk about punch cards at this point. And before I go any further into reminiscing about how awful computers were in those days, let me tell you about the very first piece of work I was given. Was to, they said, Stuart, we've got this model, it's called the Jaguar control model. It models the whole of the Jaguar car company, about 40 different plants and production facilities, all interlinked. And the aim of this model is to help them better plan the production across all of these different facilities. Stuart, here's the code on paper, looking something like that, about 10,000 lines of code. and it was all written, if you want to reminisce, in Fortran 77. So I was then given a day's lesson. Day may be an exaggeration, maybe it was a morning's lesson in Fortran 77, and then told these are the changes they want, try and work out how to do it. I don't think we induct people into modelling in quite the same way these days, but somehow I managed to survive and managed to make these changes with some support from colleagues, admittedly, to this model. And then they dared to put me onto my first project, and they said, Stewart, we want you to go over to Jaguar in Coventry. We were sort of 30 miles down the road, and put in a quote for this model that they need building. So I was sent off, met with the production manager of the Radford engine plant. So it was around the engine production plant in Radford, which is a suburb of Coventry, and met with Jim. I think it was Jim Wilson, but I can't quite remember his surname. Jim had a slightly disturbing habit of deciding to shorten my name as he got to know me better. Now, for those who know me, I don't really shorten my name very much. Occasionally people do, and that's okay. So I started off as Stewart, then I became Stu, and we even believe once he actually dared to call me Stewie, which is definitely not a version that I use. So after all these years, I'm going to get my comeback on him, because I didn't dare do it to his face, but we're going to call him Jimbo for the rest of this presentation. So Jimbo introduced me to the problem of this plant. And basically, here we have in Radford a production plant for engines. These engines were being made for assembly to a car at another plant, which I'll say more about in a moment. Basically, at that time, they were making about 3 types of cars, the XJ6, the XJ12, and we all fondly remember the XJS. And they required, between different customer requirements, about 40 different engine derivatives. So we're talking about quite a range of different engine types that they were producing. Now, the way this worked was, we make the engines at Radford, and the cars are being actually made at Browns Lane, which is about 5 miles down the road on another part of Coventry. The way this works is there's what they call a body in, it's not body white, it's a coloured car. Let's just pretend it's a silver car there, is launched onto the assembly track, and there were 4 parallel assembly lines. And at that point, they say, this car is going to be for this customer order, and that's the first time they know which specific engine they want in the car. So at that point, they can say, I now know what the engine is, and so we can now start making that engine, send it down the production line, and once it's produced, we can then ship it off to Browns Lane, to roughly halfway down the assembly line where the engine is put into the car. All good so far. There is just one problem. It takes about 12 hours to make an engine and get it shipped. It only takes 6 hours for the car to get from being launched onto the line to the orange point. So the only way they were handling this at the moment was having a huge store of engines, ready-made engines, at the Radford plant. Which of course was a high amount of inventory, and very often they didn't have the right engine. If they didn't have the right engine, you don't stop the production line, you put the wrong engine in the car, run it to the end of the line, drive it off the end of the line, and then take it to a remedial place where you take the engine out and put the right engine in. Now that is not a simple task once you've completed the car. So the proposed solution to this was, let's put a store halfway down the line. So what we'll do, at the point at which the car is now launched onto the line, we'll order an engine from this midpoint store, a part completed engine of the right type. That'll trundle off, get completed, and sent to Browns Lane within the 6-hour window we've got. We can manage that. And what we'll then do at the same time is order a replacement engine into that store. Basically, for those who are familiar with it, a Kanban system. the question was, would this work? And the other question was, what mix of engines and how many engines do we need in that store? So I'm fairly green at this point. I mean, I've only messed about with one model I've changed, but I was asked to quote on this, and then I merrily set off on doing the work. And this is the model I produced. Okay, now you may not have even seen the slide change there, but based on the experience I'd had with this model of the whole of Jaguar, which actually represented production facilities very simply, just as a time delay, I realized I could do the same thing here. I don't need to model all 100 machines that are in the Radford plant. So effectively, I reduced this problem down to 4 key elements in terms of production. There was the first half of the Browns Lane production facility. Once the engine's in, it don't really matter what happens next. There were the 2 steps in the Radford process. So before the intermediate store and after the intermediate store, and then there was the shipping to Browns Lane. And by modelling these as effectively time delays, we knew how long it took for engines and cars to go through that section, I could simplify the model. The project was a success. We actually identified the storage need, which is roughly 140 to 150 engines, far fewer than they were storing at the moment at the end of the line. And we identified that this would have a very high success rate in terms of getting the right engine into the right car at the right time. So Jimbo was a very happy man at the end of this. The only failure, I think, in all of this was I quoted 3.5 weeks of work. It probably took about 7 weeks. So I don't think my company was so pleased because I spent a lot longer on it than we were being paid for. So what did I learn about modelling right at the beginning of my modelling career? Well, quite simply put, it isn't necessary to model everything about the system to answer the question at hand. And this really led to the kind of rule, I would say, that we work to, and many quote, of course, is you create the simplest model possible that's capable of addressing modelling objectives. Now, I basically carried on with this theme every time I went and built a new model and worked with a new company over and over again, looking for the way to create the simplest model that I could in order to address the modelling objectives. And indeed, not too far further down the line, by the late 80s, I was running training courses in simulation, mostly around the software that we sold, but also teaching them a bit about how to model. In fact, this is one of the reasons I ended up in academia, because I enjoyed the teaching element. And when I got the chance to move to academia, I thought, yeah, maybe I would enjoy that. And I started to draw this curve, and some of you will have seen this. And this was just a way of explaining to people, mostly practitioners and later students, about the relationship between model accuracy and the complexity of the model. And it's a very simple, effectively, Pareto curve. 80% of the accuracy comes from 20% of the complexity. We would love a 100% accurate model. It's never going to happen because we never know everything about the real world in order to be able to model it. And actually, I've always argued, or certainly quite quickly started to realize that you could get to a point where you put so much complexity into the model, it could potentially get worse. More on that on the next slide, just to explain that relationship further. And more recently, this has been, I've described as, well, I was going to call it the Robinson proposition, but then I discovered that a guy called Lineweber, who worked for the Rand Corporation, actually proposed a very similar relationship back in 1979. So we'll refer to this as the Lineweber and Robinson proposition. Perhaps I should have just put my name first, but that would be a bit cheeky. Now, why does this relationship exist, or why this proposition? Well, this is what I call the accuracy complexity fallacy. So ultimately, when we're building a model, when I'm talking to Jimbo or any client, we have a desire for more accuracy. And naturally, that's what we'd like. We'd love a truly accurate model. And of course, the drive for accuracy drives us towards more complexity. As we add more complexity, we would expect more accuracy. And so the loop goes on, and we can build ever more complex models. Now, if that was the true relationship, or the only relationship, we would expect that we just keep adding, and that curve, in fact, will probably be exponential in the other direction. We get ever growing accuracy from more complexity. So why is that not the case? Well, the reason is that we need knowledge and data about the system in order to support that complexity. So requiring more complexity requires more knowledge and data. When I don't have that knowledge and data, I fill it in with assumptions. So I'm now starting to make more assumptions. And as I make more assumptions, so what we get is a negative impact onto our accuracy. So what I've got, for those who are familiar with positive and negative feedback loops, is I now have the assumptions negative feedback loop pushing against accuracy. So what happens with the curve I've just shown you is, as I add complexity over time, the rate at which I'm making assumptions starts to dominate, initially reducing the benefit to accuracy and ultimately actually reducing accuracy if I go too far down that line. So then I decided to become an academic. 1992, I'd spent 6 years in practice. To be honest, got a little bored of going to the next company, building the next model, and I was looking for a new challenge, and that came through Aston University offering me a teaching post there. By nature, what I started to do when it came to the research side of my career, and I actually went and did a PhD part-time while I was at Aston, realizing quite quickly I needed one of those if I was to stay in academia. I focused on this interest I'd had from all this experience in how do we develop models. And more specifically, wasn't really interested in how do we code models. Do we use Fortran 77? Well, no more, but what coding do we use? But actually the underlying idea of how do we come up with the concept for the model. So when I'm presented with a problem, when I have a client in front of me who says, this is the problem, somehow I translate that into a model, which I'm then going to code. And this is what we know as the field of conceptual modeling, coming up with the model concept. So I'm going to just do a little bit of theory for a moment. And then what I want to do is to come into some discussion about some key lessons about how we model and some examples, stories to go alongside that. So actually fairly recently, I did a bit of diving into the philosophy of modeling in the philosophy of science. And I came across this guy, Guerre, who describes modeling in this way, which I think is really very useful. So S, who is an individual scientist, in our case, a modeler basically, uses X, which is the model, which can be in many forms, to represent system W for the purposes of P, in order to answer a question, understand something better. And what Guerre argues is that actually it's not the model that's doing the representing, but actually it's the scientist who's using the model who is doing the representing. And for me, if we follow that through, it follows that the model artifact, X in this case, exists within the mind of the modeler, scientist S, and anything else, model code, model documentation, the computer model, are all representations of that artifact. And it's quite important, the basis of conceptual modeling is the model concept exists in the mind of the modeler. And this is actually the thing that's fascinated me all these years, is how does that modeler come up with that concept? Because some modelers come up with great concepts and some come up with some pretty rubbish concepts, if I'm honest. So how do we do that? And how do we improve the way in which we do that? So conceptual modeling kind of existed already, but wasn't well written about or researched. Most people like to look at coding or look at the mathematics and statistics of analyzing output from simulations, but very little on this element. So I set about saying this is something I'm going to focus my attention on. And in fact, major milestone for me was 2008 when I got 2 papers actually published in the Journal of OR on this subject. They took me 8 years to get published. So anybody here who's struggling online, struggling to publish, persist, okay? It's really important to do so. So this is my definition of the idea of conceptual model and what we mean by it. I'm just going to highlight some bits from it. First of all, the conceptual model is not software specific. So it doesn't matter what software, what coding approach I'm going to use. The conceptual model is not specific to a particular type of software. It describes the computer simulation model. Now, I highlight that because actually there's some confusion in the field. Some people say the conceptual model is a model of the system, rather how I understand the system, rather than being how I understand the simulation model. And in a moment, I'll show you that there's a big separation between those two things. So it describes the computer simulation model. And then a slightly curious term here that will be is or has been developed. Why have I put that in there? Well, I want to go back to my Jaguar engine plant model back in 1986, 87, when I was working on that. The first meeting I had with the production manager at Jaguar, as soon as he started talking about the problem, I started to form a model in my mind. How am I going to approach this? And I was thinking about the model that will be developed. As we went through the project, it was a model that is being developed. And today what I've done is I've explained to you that model. Probably not completely accurately, because I'm thinking 34 years ago, but 40 years ago nearly. I'm thinking way back then as to the model as I remember it today. And actually my view of that model will have changed over time. So I can still reconceive that model today, a model that was developed nearly 40 years ago. And the last bit of that definition is about what it explains. I won't go into too much detail with that, but it's about the objectives, inputs, outputs, content, assumptions and simplifications of the model. Now, a useful way I find to explain how this works is through what I describe as the artifacts of conceptual modeling. So let's just think about and build this diagram up with reference to the Jaguar model that I've been talking about. So I go to a meeting with the production manager. He explains the real world to me and the problem that is to be addressed in that real world. What I am doing during that is I'm acquiring knowledge about the system and I'm forming in my mind a system description. So we've gone from a sort of fuzzy cloud to a nice box, which is everything I know about the system that I'm going to model. But along the way, there are things Jim doesn't know, I don't know, nobody can necessarily get at. So we realize we start to make some assumptions about how things might or might not work. Now then, the most important step in all of this, and this is where it goes wrong so often, is we then drop into the model domain from the problem domain by conceiving of the model. And the importance part of this step is model abstraction, is how I abstract away from the full system to a simpler version, an easier way of modeling it. Think back to my two diagrams of the problem. I explained the problem to you. The next slide showed you the conceptual model, the simplified representation of that problem. And this is an important step where we put in simplifications, deliberate choices to model the world more simply than it really is. Note, people often say assumptions and simplifications as if they're the same thing. They are very different. Assumptions are filling in gaps in my knowledge. Simplifications are deliberate modeling choices to make things simpler. To complete the loop, Once we understand the concept of what we're modeling, we design the model code, we code it to create a computer model. That becomes my simplified representation. So what I've got here is conceptual modeling is kind of right top of this diagram. And the executable model, we might call it, is the model design and computer model. So the arrows here are showing flows of information through this process. It's not, I get the system description, then I conceive the model, then I design the model. Very much we iterate around all of this as we go along, something I'll say a little more about in a moment. So let me return to the practical and 5 lessons I'll get through reasonably quickly about how we model. First lesson, in fact, I've already done. And that is, we do not model everything we know about the system, because it won't necessarily be more accurate and it will take a lot longer to complete if we try to do so. And refer back to the Jaguar engine plant model that I talked about earlier. Very clearly there, we didn't model everything we knew about the system, we simplified it down. And I believe fully that that was a suitably accurate model and they implemented the findings. Second, and very much aligned to that, is the point that we simplify, we simplify, we simplify. How do we simplify? What's the trick to simplification? Well, the trick is not to focus on the system we're modeling, but to focus on what is the problem and the decision we want to make. As soon as we start to do that, we can see elements of the system we don't need to model, don't even necessarily need to understand. We focus on the decision being made. So a little story about this. In my days at Warwick University, one of my colleagues once came into my office one day in a slight state and said, "Stewart, we've got a real problem where I live. They want to build a new nursery school on our road. And we just don't think there's room on our road to have this. It's going to have cars everywhere, people everywhere. It's going to mess up our street. We're going to put in a complaint about the planning application. Can your simulation thingy help with this?" was her comment. So I looked at it and I said, well, yeah, possibly. So in fact, I said, it's fine, but I'm doing this in my kind of spare time, which I don't have a lot, and therefore I can't model every detail about this problem. And that sort of transposed, I did the work, I'll say more about that in a moment, but I did this work, but that transposed then into me creating a case study around this, which actually morphed into what became known as a conceptual modeling challenge. And you can actually find it, strangely, published in the Society for Computer Simulations Modeling and Simulation magazine as the Happy Faces Daycare case study. That's because it got kind of North Americanized at that point. Anyway, this is the British version, I have to say. And just briefly, here we are. We have a road called King's Road. It's all been hidden, exact names of everything here. Nursery school you can see on there. There was a cul-de-sac off that road. And basically this road sandwiched between 2 main roads. And the worry was that cars were going to sort of be littered everywhere and people couldn't get, the residents were going to be unable to get out of their street or be unable to park in their street even, particularly at peak times. So I was left to think about how to model this problem. And the reason it's become a bit of a case study is actually I use it quite a lot when I'm training in simulation, and you give it to people and say, how would you model this? And they come up with the most fantastic models, which would take weeks and weeks to develop. Whereas what I had to do was boil this again down and simplify it right down into a much simpler version. And this is what the actual model looked like, very simply without going into the full detail. It recognised there's 3 types of cars. There's residents, there's cars going to the nursery school, and there's cars that use it as a cut through the street. And there are basically 3 causes of congestion. Those who are waiting to park in the street, primarily people coming to the nursery school, and then those who are trying to turn out onto the two main roads. Those are the blue circles. So those are queues of people causing congestion. And the activities, the things that these cars do, are drive along the road, park in the road, turn out onto the two outside roads, the two main roads at the end. So we boiled the whole problem down to 3 types of cars, 3 queues, 4 activities. Doesn't need a lot of data. Knock the model up in a matter of 2 or 3 hours. They had the data already, so I could do this work in roughly a day. And I could then predict the size of the queues for waiting to park and waiting to turn out at a peak period of the day, Monday morning, let's say. And then we could identify where we're going to have large numbers of cars littering the streets in this area. Very simple model, developed very quickly, answered the question. Only problem was, said, you're not going to actually have a problem. So I wasn't very popular, didn't really help their case. Lesson 3. There are many potential models we can develop of the same system. And indeed, if we give the same problem to multiple modelers, they're going to choose very different models. Way I can put this is, here's the real world problem, here's the system description. So let's say we can give a series of modelers the same system description and then say create a model from it. There are effectively, as indicated by the bottom line there, probably an infinite set of conceptual models, an infinite number of ways of modeling that same system. And if I ask one modeler, they might choose model I there. And if I ask a second modeler, they might choose model J there. Now, this was very much highlighted to me, and it still remains possibly one of my most favourite pieces of work I did with John Moorcroft from London Business School, who is an expert in a slightly different form of simulation. I, technicalities, do discrete event simulation primarily. John Moorcroft was an expert in system dynamics. We both build simulation models. And what we decided to do, because I said, well, you do things differently to me. Let's look at how we, compare what we do. So the way we did it in the end was we said, look, there's a standard problem called the fisheries problem. Basically, it's looking at overfishing. Here's 2 examples, the Pacific sardine catch and how it was overfished and collapsed and never returned, and the North Sea herring catch, which was overfished but actually managed to return on the bottom there. And what we said was, look, we know what this problem is. We'll go away separately and we'll build a model of this same problem using our particular approach to modeling it. And basically what we were looking at is the fishing element, the fish in the sea, and what was happening was the fishing fleets that were going out, the ships that were going out to fish. And somewhat colloquially, this was known as the fish and ships model. So we independently came up with the models. Again, I don't want to go into the detail here, but this is a sort of representation of John's model using a system dynamics approach. John's worldview, when he's presented with a problem, is that the system behavior is primarily a result of information feedback. In other words, if I go out fishing and I catch lots of fish, I think there must be a large fishing stock. So I'm going to take more ships out and fish even more. Of course, you can see the problem here that by the time you stop having so many fish, it's a bit late. So there's a delay in the information that's coming back to you. And this is what drives system behavior. My model, don't need to be an expert here to realize that looks somewhat different. Same problem, me looking at this differently. My worldview is that the system behavior is primarily a result of random events that in some way interconnect. So some days I'm lucky and catch lots of fish, some days I'm unlucky and don't catch many fish. So there's an element of chance within life, and that can lead to all sorts of outcomes. So we created these 2 models separately, and then we ran them for results. So what did we produce? Well, interestingly, this is John's model. If you look at line 1, which is the line that kind of drops off on his graph, it looks pretty close to the Pacific sardine catch. If you take my model, it moved into an oscillation, which actually looks quite similar to the North Sea herring catch. And if you ran it on, actually, it did go almost down to 0 and then back up again. Now, you might say, which model's right? Well, neither model was right. I mean, they're both quite simple representations. They were built from different worldviews. But the point was that we were, through different explanations that we modeled, able to represent behaviors that you see in practice. So neither model was right, but neither model was wrong either. And to me, the most important thing behind this was the fact that we chose to model the same problem in very different ways. And so if we ask why do modelers choose different models, well, we don't really know, but part of it is about their worldview, how they approach looking at the world. Part of it will be their training, part of it will be their experience, and part of it will be about their cognitive processes. And little cue for anybody younger here who's interested in modeling, if you want to do some research, that would be an absolutely fascinating thing to understand the cognitive processes that led to different types of models. Lesson 4, I'm doing all right just about for time, so we'll get through our lessons and a bit of a conclusion at the end. Lesson 4, we iterate a lot between the different modelling activities. In fact, if we take this to the conceptual model, we are constantly refining the concept of the model as we are working through the modelling process. And even actually, if we don't change the computer model, we might well still be thinking, actually, it would have been better to model it this way rather than the way that I am. Now, again, it's a project I enjoyed, though I have to give credence to my colleague Antuela Taco, who did a PhD with me on this, who's now professor at Nottingham Trent University, was we wanted to look at how modelers went through the modelling process. And we did this by actually giving them a standard problem with modelling the prison population in the UK, and then spent about an hour building a model in front of us. And we did a thing called verbal protocol analysis, which meant that Antuela sat in the room with them and said, talk about what you're thinking as you do it. So we had an hour's transcript, roughly, of what they were thinking about while they were building the models. And therefore, we could analyze those transcripts. And just to show you an example of one of them, this is the timeline for one of the modelers that we worked with. And it splits modeling down to a series of activities, structuring the problem, conceiving the model coding, data, validation, results, and implementation. Nothing in implementation because this wasn't a real problem, so they didn't actually ever seem to think about that. But look at the number of transitions between these different activities while they're modeling. On average, we were getting about 100 transitions in an hour between one activity and another, which is both forward and backward. If this was not an iterative process, they do all the problem structuring, then they do all the conceptual modeling, then they do all the model coding. That isn't the case. And notice how they return 7 times to the conceptual model, and even really quite close to the end, but going back and obviously questioning how they conceived the model. And so we see a lot of iteration, say very similar pattern with every modeler that we worked with. And lesson 5, we emphasize learning as the goal of modeling and not accuracy. Of course, we may need accuracy to learn. I was part of a team of 4 people that worked with Ford Motor Company on designing a new engine plant. At one point, I was the world's expert on engine plants, I think, or modelling them. A major project, some parts reasonably quick, but it was actually a 2-year period that we worked with them, helping to improve the design of this plant. That was a very major investment. At the end, I was asked to write a report for the senior manager at Ford, who was famously quite a difficult person. Anyway, so I wrote this report, all these things we'd learned and told him, Anyway, I went down to present it, and he listened duly, and then he sat and said, Stewart, the problem is that we could have done all that if we'd thought about it. And I said, yeah, but the problem is if you didn't have the model, you would have never thought about it. And the point was that the model was the catalyst in that case for learning and improving the system. Absolutely vital to what we do. So, bit of a bonus lesson. Let's return to the beginning. The Line-Weber-Robinson proposition. And I subtitle this, Don't Believe Your Own Propositions. Finally, I long thought I must have a look at this because I've been spouting this for years without the jot of empirical evidence for it at all. Just seemed sensible and nobody ever argued with me. So I finally, just before I started the role here at Newcastle, had a sabbatical and spent a bit of time looking at this problem. And what I did was to take, to start with a fairly simple model. It was 100 machines connected by 100 conveyors. I modeled the whole 100 machines and 100 conveyors, and then I gradually, successively simplified it by creating blocks. So I took a block of 10 machines and converted it into a time delay, and then I took a second block of machines and converted it into a time delay, just to make it a gradually simpler model. And what I was able to do through this was to measure how the accuracy of the model changed as I simplified it from the initial state. So the way I was measuring accuracy is I was measuring the absolute error. So it didn't matter whether the error was plus or minus, but how the error was different to the original model. And big problem is, how do you measure the complexity of the model? The simplest way I found to do it was measure how quickly it runs. More complex, more difficult models run slower. Simpler models generally run faster. So basically, if you think, what was I expecting to happen when I did this simplification? I was expecting a curve that looked like that. It's basically the flip of my accuracy curve. What I'm expecting is, as complexity increases, the error shrinks as I go along. So a low accuracy model on the left end, a low complexity model will lead to a large error. A high complexity model would lead to a low error. What happened? Wow. I'm exactly right. After all these years, it looks almost perfect, doesn't it? So I thought, well, that's great, but let's try another model. So I took another manufacturing model, and it didn't work so well. And this actually was a model which is a case study in my book. Mention the book again, 3rd edition out. Is a model, and what I was doing was taking out gradually various details from the model. So it wasn't doing this kind of blocking like I just did with the other model. It was another format. And I tried it in a couple of different ways, and I got equally weird patterns every time I did it. And then I decided, let's have a look at a more sort of service model. We won't go into the detail. I got a really weird pattern here. So it got worse, and then it got better as I simplified the model. So what do I conclude from all of that? Well, I conclude that the whole proposition I've been spouting for nearly 40 years is actually not correct. Probably fairly obviously, because it was a fairly simple heuristic. And of course, that curve depends on the specifics of the model and the nature and order of simplifications that I put into the model. However, not put off, and I would still say, I think the actual proposition itself is a useful heuristic for guiding modelers when considering the scope and level of detail of the models that they're building. And again, an encouragement to build the simplest model possible to address the question at hand. So just in closing, I just wanted to say a few words about people in my career. And sort of reflecting my career, I think there are 3 types of people you need. You need people who inspire you, people who provoke you, and people who work with you. So 3 characters I'd like to mention. Mike Pitt was my PhD supervisor, who actually taught me as an undergraduate, and I got my worst result in my whole degree for the simulation coursework in my year 2. Didn't put me off my career though. But Mike is very much important in terms of helping me think more than just simulation is coding or analysis, but thinking about the context and the way we work. Sadly, no longer with us, but Ray Paul was actually my external examiner, but continued to work with him. Ray was a major force in the simulation field, and all I can say is you don't say no to Ray if he suggests something. So, a lot got done because Ray was, and actually put a lot of faith in me. And the third character, I don't wish to embarrass you, Simon, but Simon is here today. I'm very pleased to see Simon. My partner in crime, we've done a lot together we met in 1995. And I would say that probably the simulation community in the UK is in by far the strongest position than because of the work that we were able to do back in those foundations. And our major success, isn't it, this year, is after 60 years of the conference being basically American-based, we've got the Winter Simulation Conference coming to the UK, which I see as a major international conference. It's rarely been outside of America, and we finally got it coming here. But thank you, Simon, for all the work. I did look, we've only ever published 6 papers in a journal together. So that shows you don't just have to publish together. And one slight, just final thing before I really do wrap up. I often wonder what my career would have looked like if I hadn't done what I do. And of course, for anybody who's in the operational research field, you have the same problem I have, which is what do you do? Operational research, what's that? So sometimes I resort to I do modeling. And actually, yes, exactly creates that response. So I've always wondered what it would be like if I had a modeling career. And finally, thankfully, due to a friend of mine who runs a shop in our local town, she needed some people to do some modeling for her on the high street one event, and asked me, in fact, I was cajoled into it, I have to admit, to do some modeling. So I truly got the experience of modeling last year. I'm a professional model. I got a £25 voucher out of it. I don't recommend it, okay? That's the only thing I can say. So I'm going to finish by just putting up the 5 lessons of modeling and to thank you for listening. Thank you.
Thank you very much, Stewart. Let's give a round of applause. I heard it from the audience. Thank you very much for excellent and entertaining talk. I bet some people will start calling you Stewie, but okay, we'll call you Stewart here. Are there any questions from Newcastle first, please?
They're being very shy at the moment. Do you want to pick one up online, and then as we'll get Simon? Oh, we've got Simon actually coming in.
I thought of this before the talk.
Right.
Well, I'll keep it. First of all, absolutely excellent talk, Stewart. Thank you very much. And I'll overcome the embarrassment one day. What's your thoughts on this and all the machine learning models that we're seeing cropping up all over the place? Do they fit your 5 rules, or can they learn from them?
Thank you. I think it's a very good point. I mean, my worry, and it was a bit with big data before that, is they all create what you call the possibility factor. So we can create larger and larger and more complex models. I think the problem here, and the key to this, is the intelligence is not, here's a system, let me model everything of it that I know. Intelligence has to come, how do I fit this to the problem I'm trying to solve? Now, I assume, I haven't played with it, but AI, machine learning can learn to do that. So I think the danger is, do we ask it to do that, or do we just say, build the most wackingly large, complex model that we can? I always say I was advantaged because of the grotty computers I worked with, state of the art in the day. I couldn't build a model of everything because we couldn't fit it on the computer. The problem now is you don't have to have that discipline imposed on you. So I think my answer to that is we need to teach machine learning, AI, to follow these 5 lessons.
I just wanted to
just so people can just so people.
I just wanted to be the first to say daytime TV. Yeah.
Right. No.
First daytime.
No,
TV.
I don't know if I got that. I won't tell you. But no, it wasn't daytime TV. That was predated that, I think. So, breakfast TV had already started, I think, at that point. But good try. Sanya, is there? I realise we're quite coming towards the end. Sanya, is there anything online that wants to come through?
There are many congratulations to you,
Right, thank you,
Stewart. I can just read emails maybe from Mahdi, from Kati Kotiadis, from Colette Fletcher, Lucy Morgan, Graham Rand. Are there any more questions, please?
We do have 2 online questions in the Q&A, Sanya. So the first one is, how do you know in practice when a conceptual model is complete enough to move to implementation?
The answer to that is you don't. And I mean, I think that's the iterative nature. Is you start to build a model, you start to conceive the model. You think you've got an idea, you start to turn it into code and create the executable model. And then actually you reflect on it. You also take it and discuss it with the client, learn more about what you've got right, what you've got wrong, adjust your conceptual model, and then recode or add code and develop it further. So I think it's pretty impossible. Though I understand, very large scale projects, you have to get as close as you can to a full specification up front, because you might have a team of people modeling, but it's pretty impossible to do that. You have to have an iterative process to get to your final model.
Thank you, Stewart. And then the other question is, I would like to know your opinion of how digital twin models can affect complexity of simulation models.
Ooh. Yeah, I struggle with digital twins. I mean, it's a term that's overused. A lot of them are simulations, they're not digital twins. I mean, a true digital twin is actually running real time against the actual system. Is it possible to have a digital twin that's so accurate it can answer, and so such high fidelity it can answer any question at any point of time about the real system that you need to improve? I think you have to still have simplified digital twins that are there for very specific questions, like what's the best schedule to run today? When you start moving into real-time decision making, I'm not saying it shouldn't be researched, but I think it's a very vexed area to get a model that is actually that accurate that it's able to work in that way and make decisions quick enough to help you adjust the system in real time. So I'm a bit of probably a Luddite in that respect, but I do think it's something we need to research and understand better.
Thank you. Are you happy to take one more? I'm conscious we're overrunning, but there's just one final one that's come in.
Oh, and I'm happy to. So people can log off anyway. They can't leave the room because I'm looking at them. But go on.
Thank you. So I'm curious why your definition of modelling omits behaviour. I've thought of behaviour as the difference between a description, brackets of a situation, and a model, brackets that can predict.
Actually, I wish you hadn't asked that question. I haven't thought about it. I mean, we embed behaviour in models. So to me, it's part of we understand behaviour in the system description, and we need to model behaviour, and we regularly do in some form or another. I mean, the problem with modelling behaviour, again, it's something we have to reflect on and simplify. So I'm not sure I'd include behaviour in the definition element, but actually see it as part of what we come up with when we define a model. So if you saw the definition of a conceptual model, it would have the actual, for a problem, rather than my theoretical definition, the conceptual model for the problem would describe elements of behaviour within it. I think I've got to stop answering questions there because they're getting more difficult.
Super. Thank you, Stewart.
Okay, neighbours.
We just had the answer to the quiz. I'll see if somebody's answered it online first. Sanya, over to you, I think.
First was Live Aid or The Great Storm, or BBC One started full-time broadcasting, or Channel 4 started.
They're all good answers. I know Live Aid was 1985.
In history.
So no. So I'm hoping somebody's answer. Well, they've got one answer here. Not sure he really wants the book. The actual answer. It was the first showing of Neighbours on British TV, which then ran for the next 35 years. I've outlasted it. The Australian soap. They brought Kylie and Scott to our screens.
So does it mean that nobody will get your new book?
No, I've got one right answer in the room.
Oh, okay. Okay, just to let you know, you have many congratulations and thank you from Dobrila Petrovic, Christos Vasilakis, Gilberto Vusu, Christopher, Sofia Baruva, Panikos Frangos, and Thanos Alifiantis.
Thank you very much.
So I think we can close the presentations, the Beale medal this year. Thank you both presenters for excellent talks. We all enjoyed it, and have the rest of the evening, pleasant rest of the evening with provocative statements from our two presentations. Thank you very much.